Hello everybody, my name is Koy Motita and today I'm going to do a paper review on DACAPO, Automatic Bootstrapping Management for Efficient Fully Homomophic Encryption. To start with, homomorphic encryption emerged as a promising solution for privacy-preserving computation in an untrusted environment such as financial field, healthcare application, and a third-party cloud and such. Since homomorphic encryption allows for the computation on encrypted data and the result that we get back is identical to the computation on an unencrypted data, this was a perfect scheme to be used. After the breakthrough by Craig Gentry, many other scheme and library was proposed and one after another. And one of the scheme which is recently proposed is RNS-CKS, which stand out as a particularly well suited for a privacy-preserving machine learning application. So when using or optimizing a long fully homomorphic encryption or FHE with the manual bootstrapping placement, it can be very challenging. Firstly, the developer must identify the growth of the scale of the ciphertext and then insert at the right place for the bootstrapping operation. Secondly, the bootstrapping operation is extremely costly in terms of latency. Since it is expensive, the developer must minimize the number of operations needed while preventing the overflow of scales. Thirdly, the placement of the bootstrapping affects the behavior of the rest of the program because bootstrapping resets both the scale and the level of the ciphertext, so it changes how the future operations behave and how long they will take to compute. So this work proposed DACAPO, the first automatic bootstrapping placement compiler that placed bootstrapping operation to minimize the overall latency in the FHE program. So to reduce the number of time bootstrapping is used, DACAPO analyzes the live out ciphertext and it's also find a program point where they check for the live out ciphertext that remain unused for a certain period of time that does not need bootstrapping and then categorize them as a bypass edge. And then DACAPO exclude this bypass edge to get a more accurate count of where the bootstrapping operation is actually needed. So to start with, I have to explain a little bit about ONS-CKS. So the process of ONS-CKS is mostly the same as CKS. If you already know, it's uh, a scheme that operates on a bunch of mini errors. So because honest is just a variant of CKS, that's why it's mostly the same as CKS. So a little bit about honest CKS is that it's introduced encoding and encryption parameters n and q, which is n is the degree of the cyclotomic polynomial that is used in the ring. It's determine the number of slots and the security level. So the larger the n, the more secure, but it's slower. Usually the n we only use about 2 to the power 15, but in this paper they use 2 to the power 17, which is quite really high. Another parameter is the q, which is the product of primes. We call it mostly chain modulus or coefficient modulus. It's determined how big the polynomial coefficient can be, and then it's used to control the maximum depth and precision. So both CKS and honest CKS encrypt the plain text into ciphertext as a pair of polynomial using this formula. So in honest CKS, every ciphertext has a scale and level property. The scale is the scaling factor, which is around 2 to the power 40 for precision control, and the level is the number of scaling factor that is available in the ciphertext for multiplication depth. So if you have a 10 of the prime, which is a chain modulus, after each multiplication you have to rescale the levels so that you drop one prime from each of the multiplication. So after 10 multiplication there will be 0 level. That means you drop 10 prime already. That's why you need bootstrapping to reset the scale and the levels. So in honest case operations such as arithmetic and rotation, it can be done with either between two ciphertexts or between a plaintext and a ciphertext. For addition operation, it requires the levels and the scale of the two ciphertexts or the plaintext or the ciphertext to be the same level to produce the ciphertext of the same level and scale. While the multiplication operation require only the level to be the same because the scale of the resulting ciphertext will grow exponentially, double every time it's multiplied with each others. While the rotation operation performs a circular shift on a message vector by a given offset. If we set the offset by 2, the first value or the first slot will rotate to the last two slot of the whole ciphertext, which dictated by the n value, which is the n parameter. In on-SQS operation, there is called a scale management. They have many various ways to manage the scale. Mostly, we sum it up as a few of them is upscale, which is an operation that make it easier to read and write, but doesn't introduce new functionality. So it's allowed the ciphertext to scale from its own current scale to another for doing calculation. So it can only apply to addition operation. So when the two ciphertexts has different scale, it can either rescale one of the ciphertext or upscale the other so that it can have the same scale or close enough to do addition operation. While another one is called mod switch. So it's in our term, it can be called mod down, which is this function allow the reduction of the ciphertext level by dropping a prime from the modulus chain. So this is useful when the ciphertext has a higher level than the other one, and we need the level to be exactly the same for doing multiplication. So we actually drop one of the scale from that ciphertext, the level, sorry, from that ciphertext to do multiplication. And the second most important operation is called rescale. So rescaling is during multiplication, the scale of the ciphertext become exponentially double. So it's double every time it's do multiplication. So to avoid the overflow of scale, it would require to rescale back to the original scale, which is closely to the original. So we divide the coefficient modulus chain by the scale that was used, so resulting in decreasing of the scale by SF, which is this case is the current scale. Unlike mod switch, it's also reduced the level of the ciphertext. So when rescaling, both the scale and the level drop by 1. So we drop 1 prime and drop 1 level at the same time. So we can only use this scale if the current scale is higher than the minimum scaling waterline, because we set a certain scale so that when we rescaling and do multiplication, there will be a certain point where we cannot do it anymore because bootstrapping requires certain levels and a certain scale. So this is the important most scale management operation, which is called bootstrap. So during the operation of multiplication, the rescaling ciphertext can be exhausted, eventually consumed for the operation impossible due to the scale overflow and no modulus prime to be used for rescaling. So the solution is to insert bootstrapping operation. So each bootstrapping operation consumes a certain level of ciphertext. So it's better to save some modulus prime for bootstrapping. In these studies, the bootstrapping operation consume certain level of ciphertext. So that means we cannot do operation after the level drop below 13 because we need to bootstrap. And since bootstrap is powerful and expensive on the latency, we can see that it's the one that consume a lot of time to do bootstrapping. That's why it need to be modified and mandate so that it can help you run your program faster. So the observation and insight in these studies is there's 2 observations and 3 insights. So a simple accumulated scale analysis may introduce unnecessary many bootstrap operation. So we don't need that many bootstrapping. So a ciphertext liveness analysis can help introduce that number of bootstrapping operation. A long-lived unused ciphertext, we call it a bypass edge, is unlikely to require bootstrapping, so it's often profitable to extrude them from the ciphertext. So another observation is that different bootstrapping placement may lead to widely different end-to-end because bootstrapping may allow for other honest operation to perform at the lower levels. A cost-aware bootstrapping analysis is needed for this performance to be understood. So DACAPO consists of 2 candidates component to be exact. So the first one is candidate selector, which consists of liveness analysis, bypass edge analysis, and candidate filtering. Another component is the bootstrapping planner, which consists of cost estimation and the bootstrapping insertion point selection, which allowed them to able to select where to place bootstrapping operation in each point of the program. So in this part, I will explain a little bit of how DACAPO works. So as you can see, we have an input right here, X, and then it goes into 3 more channel of the first convolution. As you can see, each channel has its own operation, which is called a live out ciphertext. Then if we have 3 channels, that means there's 3 live out ciphertexts. So that is count 3, 3, 3, and 1, because at the end, all of the 3 live out ciphertexts combine into 1. So this one will continue on forth. But you can see there's an arrow here, which I will explain later. For now, it's going to another into convolution 2 and do the same operation. But now we can see that there's 4. Even though there's 1, it's already go inside to operate in here, there's 4. If we continue, then there's up to 2. But then it's go to calculate into an activation function, and then it's go back to 2. But somehow in here you can see that after it's go to convolution 3, there's only 4. Why is that? Because right now this 1 is already been destroyed by going to in this convolution 3. It used to calculate the others, so that means the 1 became to this become 3, 3, 3. But since it already have 1 over here, it become 4 again. So it's become 2 at the end because we had to add them together. And then finally, after this one, which is the long-lived ciphertext or bypass edge, it does not use for a long time until this point. So we have another 1. So as you can see, a bypass edge operation, you can see this one is 0 because we don't count them. Because as I told you before, the bypass edge has to be excluded to make it work. So you can see this live out ciphertext around here. So as we can see, when the valid live out analysis, we can see that this point is also a candidate for bootstrapping selection. All these are 5 from C1, 2, 3, 4, and 5. So when the bootstrapping planner happen, it's run every single possible scenario where they boot the first bootstrap, and then you can see the latency. And then if they run the bootstrap on the C2, and then we can see the another latency. We can just look at the final test, whereas they done everything. The first one, since it's already bypass edge, we don't need to bootstrap, and then we bootstrap the next live out ciphertext. And then since it's already just been bootstrapped, we don't need to bootstrap it again, and then we skip it. After doing every operation, we can see that we should also have a bootstrap here, but since the operation end with addition, it's not multiplication, so we don't need to bootstrap. So this why this has the lowest latency possible. This is what DACAPO proposed. So the setup is that they evaluate with 12 deep learning model using different activation function like as pooling strategy. So the network that was used was ResNet 2044, AlexNet, VG16, SqueezeNet, and MobileNet. While the hardware that was used was Intel i7-12700 with a GPU of NVIDIA RTX 3090 with 24 GB VRAM. The experimental setup is that they compare with DACAPO and 3 DACAPO variants. First is the human insertion placement. The second one is the liveness place bootstrapping with the scale exceed capacity using live analysis. Third is the bypass excluding all bypass edge. And fourth is full combine everything together into one. And you can see that the DACAPO can achieve almost higher than other methods. Not by much, but just by a little bit. The accuracy of this performance was estimated to be very high because the y and the r squared is closely to 1, which is shown as very high, while the variance minor different from the memory transfer using UVM. So since the GPU had the 24 VRAM, so it requires some more memory to do this operation. While the key insight is that its added latency from the UMV doesn't harm the bootstrapping placement, which is good because the penalty is considered to be consistent for the same benchmark for every single network. So the performance was still remain valid for every test that they done. So to conclude is that this paper introduced the first automatic bootstrapping placement management compiler, DACAPO, which efficiently restrict bootstrapping candidates through live-out analysis, while also considering the bypass edge that should be ignored and removed. DACAPO also find bootstrapping placement plan with minimum cost based on this candidate. So the results show that DACAPO consistently outperform manually implement FHE program on deep learning models, of course, and it's also achieved a speed of 1.21 times faster than the manual baseline. And if you want to check the code, you can go to this GitHub repository here it will contain everything else. So this is the end of my presentation. Thank you.